Hi. So we're dealing with, I think it's chapter 4, is it? The algebra in the Islamic world. And so what we're kind of doing is kind of looking at the development of algebra so that we can almost say it's the invention of algebra as kind of we know it. We've seen, though, that people did algebra-like problems, but it wasn't the algebra like that we do, like in, say, if you look at pre-calculus class. So what kinds of algebra you do there? You do things like doing stuff with polynomials. Sometimes you find roots. Sometimes, you do multiplication of polynomials. And, you can even do division of polynomials. All that kind of thing. So what are we going to do is look at the development of algebra, and we're going to kind of see it sort of starting with Al-Khwarizmi, who we've talked about before. He was the guy who wrote this sort of the textbook sort of introducing arithmetic, so using the Hindu numerals, which we now call Arabic numerals, because they did such a good job of putting it forward with all the algorithms that they had to do the arithmetic that we do. And he also wrote the first book on algebra. So this is going to be a story which goes from around 800 to around 1100. And it's kind of corresponds to kind of the height of the medieval Islamic civilization in Baghdad. So it's when the Abbasid Caliphate was kind of very powerful, and at the same time it was a patron of science and art, and particularly mathematics. So they had what we would actually call universities. So it was the House of Wisdom in Baghdad. They started institutions which we would basically think of as universities. So for example, there's a famous university in Cairo, Al-Azhar University. I think it's the oldest university in the world, and that was kind of like the model that the medieval universities in Europe did, the famous ones in places like Bologna and Oxford and places like that. When they started, they were modeling on that system. And so we're going to see algebra sort of go from something, it's going to start off kind of very geometric. So it's kind of like very much influenced by how the Greeks did algebra. And by the end, it's going to sort of turn out kind of more like how we would recognize algebra to be. Some things are different, not like what they are. For a start, all throughout this period, everything is rhetorical. Everything is done in words. So even like in writing out numbers, they write out whole, use the words for everything. So everything is a verbal description of what's going on. Okay, and at the moment I am sending out emails about the third presentations. So one of the things that we'll see in the third presentations is the introduction of the notation to do algebra like how we do it. The idea of using symbols for variables and constants, using things like plus, equals, minus sign, all those things need to be invented. So they're not around back at this time now. Okay, so let's look at, so let's have a look at quadratic equations. Here we go. Good. Okay, so let's start off with the quadratic formula, and this is something that was heavily influenced by geometry. Okay, so let's do a little bit of analysis of the quadratic equation. So let's kind of look at it with our eyes and see what we can do with that. So we all know here's a quadratic equation here. This is the general form. This is how we would view the quadratic equation, with coefficients for the x squared term, the x term, and the constant. It's just more convenient to deal with monic polynomials. So let's divide through by the leading coefficient to get x squared plus dx plus c. Okay, and so if you do the quadratic formula, okay, here's what we get. Sorry, I used minus plus instead of plus minus for some reason, I don't know why. Okay, now we want to interpret this geometrically. So we've got to look at the operations and think about geometric things. So one of the things that gets us in the road of us, in the way of us, is this dividing by 2. Okay, so what we're going to do is just going to bring the 2 in, so it becomes minus b on 2. Putting dividing by 2 inside the square root means dividing by 4 inside there, so we get b on 2 squared minus c, and we see that this actually simplifies the equation a little bit, right? Because we've got a b on 2, we've only got 2 things, right? We've got b on 2 and we've got c. Okay, so what we're going to do geometrically is we're going to interpret things as lengths and areas. So x is going to be a length, so that means this has to be a length and this has to be a length. Okay, so geometrically we have to worry about whether b is plus or minus, right? So if b is minus, then we want to look at minus b. If b is positive, then we just want to look at plus b. So this is going to be a length. B on 2 is going to be a length. So this is going to be, these are going to be lengths of rectangles. Here we've got a square root sign. So to think of that as a length, this is going to be a length of a square, right? So that's what taking the square root means. Okay, so that means the things inside here have got to be areas. So b on 2 is a length. So b on 2 squared is going to be a square side b on 2. And c has to be an area. So it's going to be the area of a rectangle. And it all makes sense if you do a dimensional analysis, right? If this is an area, that has to be an area, that has to be an area. Okay. So this thing, whatever's inside of this thing has to be a square. This is a square, and this is a rectangle. Again, we have to think and worry about plus or minus c. We have to worry about whether c is positive or negative, because this has to be a positive number for it to be an area. Okay, so that's why when we look at it, so I think you've already done a homework problem with this, what we consider a quadratic equation breaks down into 3 cases. And there's some trivial cases as well that's also dealt in there, but let's not worry about those trivial cases. So that's why there has to be 3 cases. It all depends upon the signs of B and C. Okay. So the interesting thing is that so the scholars were highly influenced by Euclid, and so that means they wanted to prove things. And so there are 2 ways that you can prove things. There's kind of like what I want to say, an arithmetic way, you know, where you're just manipulating symbols and that. And there's also kind of a geometric way. And we've already kind of seen that the geometric way was privileged, right? They thought that if you could do it a geometric way, that is the best possible way, because then you don't have to worry about things being irrational or whatever. Geometric things were just thought to be on a much stronger logical foundation. So what these Islamic mathematicians did was they solved these quadratics, and we've seen that quadratics have been solved for thousands of years before that, like going at least back to 2000 BC. The Babylonians were solving quadratic equations. But what the Islamic scholars did was they brought together, and this is kind of like how that empire did so well, it brought together East and West for its own advantage, right? So they brought together stuff from Babylon, stuff from India, stuff from the Greeks, and they sort of synthesized the mathematics, okay? And so they wanted to prove things geometrically, and so the whole thing that worked was Euclid Book 2, which is kind of like the geometric algebra book of Euclid. And Brent, you did this, didn't you? Yeah. And so these are the two key propositions which basically they use. So proposition 5 says if a line AE is divided at B and bisected at W, then the rectangle AB by VE plus the square of BW is equal to the square on AW. Okay? And when you just say it like that, it kind of just like slips over your head and you go, well, what does that mean? In a little bit, we'll look at some of what the Islamic commentators did. They made it very explicit why this has to do with the quadratic formula. And so what is it? So proposition 5 says you've got an AE, you divide it at B, so B is kind of arbitrary. So you're given AE, and you're told that you need to divide it at B. So that's kind of like your unknown right there, where that B goes. W is half of AE, and it says that the rectangle AB, so AB by BE, okay, so that's going to be this rectangle here, plus the square on BW, which is that thing there, is equal to the square on AW. We'll see in a little bit why that's true. But there's two ways you can go about doing this, right? You've got AW, you've got AE, you've halved it at W. B can be in two possible places. B could be between W and E, or B could be between A and W. So this is with a B between W and E, and over here, B is between A and W. And the idea is that you can come up with a similar picture of this for this situation right here. And proposition 6 says that if a given line BH is bisected in W and extended in a straight line BA, the rectangle AH by AB plus the square on BW is equal to the square on AW. So this is a little bit different. So here we've got this line BH, it's bisected here, and now we're extending kind of this line. Whereas before things were happening inside the interval, here the interval has been extended. But it's kind of giving a similar kind of result. And that's good, right, because we need different pictures for the three different cases that come up from the quadratic equation. So let's have a look at the main guy, Al-Khwarizmi. So remember, he's he's sort of the person that started all this. So we're talking early 9th century. And let's have a look at the equation x squared plus 21 equals 10x. Now, the way that he proved stuff was there are no formulas, right? There's no, there's no notation to write down general cases. The way that you showed stuff was you did a case with numbers, with actual things, and you went through, and the idea is then that when you get a different problem, x squared plus 25 equals 10x, say, or whatever, something of the same type, you just try and copy this method to do it. Okay, so here, when we go and look at our quadratic formula, and so that's going to be our guide, because we know this has to be what happens. And it has to satisfy the quadratic formula. So here, b is minus 10, right? Because if we put the 10x over here, we'll get a minus 10. C is 21. So we put this in here. So here we get 5. So this 5 is the length. And this 21 is the area of a rectangle. Okay? And so this is using Euclid 2.5. Okay, so what does it say? It says AE equals 10. So this is our interval, it's 10. So the number of roots becomes our interval that we deal with. So if this is a different number, you put that number here for AE. You halve 10 to get 5, right? Because this is what happens from the quadratic formula. So we halve AE at W, and so this is 5 then. Okay? This AB is going to be our X. So this is what we're trying to find. And this rectangle here is our 21. And so by Euclid 2.5, AW squared is equal to this rectangle here plus this square here. Okay, so AW is 5. This is 21. So BW has to be 2. So if this is 5 and this is 2, then our X has to be 7. Okay? And if you do the other case where B lies within AW, you get the answer 3. You're going to get 5 minus 2. So that's going to be like a homework for you to draw the corresponding picture. Do I? Nope. Why is that true? Let's go back to here. So you can kind of, let's just do an arm waving kind of proof of why this is true. So what is it? So we're saying that AH by AB rectangle did I do this right? Should that be BH, you think? I think it's supposed to be this rectangle here, plus the square on BW is equal to the square on AW. So the square on AW is also the same thing as this square here, I guess. What can we do? So I think that's supposed to be either rectangle AH by AB is equal to that, And so the idea is if you sort of cut it there, and you take this rectangle and put it on top of here, then you get a square that turns out to be the same as the square on AW. And the other one is kind of like a little bit easier. The same. Oh, sorry, I was reading the wrong thing. AB by BE. The rectangle AH by AB. H by AB. Is this rectangle here plus the square on BW, here is like here, equals the square on AW. So this, so here is AW here. So the idea then is you take this rectangle, put it over here, put the square on BW there, and that's actually completing the square like we normally do. So that's a basic reason why 2.5 and 2.6 work. But if you go to Brent's talk, you did prove 2.5, didn't you? Yeah, he did it in a very nice way. If you look at that again, if you need to look at that. Okay, so that's Al-Khwarizmi. Let's have a look at a different quadratic, and this is by a mathematician who came after Al-Khwarizmi, right? So Al-Khwarizmi was till around 850, so he was early 9th century. Thabit ibn Qura was kind of more like late 9th century. So what he did was he actually did try and do some examples, but with more general examples, where instead of using actual numbers, he actually kind of try to use the cases where the numbers they weren't actual numbers, but they were just kind of like generic number of roots. Generic. They called this the Durham because they thought of x squared as the wealth. They used the term mal for that. So they thought of this as kind of like some sort of coinage to go along the way they interpreted things. Okay, so in this situation here, Q now becomes negative, and this is positive right here. So we've got minus P on 2, and Q. And, right, so minus Q right there. So in this case here, we need to do Euclid 2.6. So in this situation here, AB is going to be x, BH is going to be the number of the roots, and Q is going to be a constant. And again, it's going to be the area of, AH. Oh, so Q is the whole thing, of course, yes.
Dr. Ryan,
Mm-hmm.
can you explain why inside your radical you have a negative P and then a negative Q?
Right.
I feel like it should be P and then a positive Q.
Yes, you're right, because when you bring this over here, you get minus Q, and so the minus is a plus, right? I think I just copied and pasted from the previous example without correcting it. Yes, you're right. That should be a positive, and so both of those things should be positive. Right, because we see right here. This gives the right answer right here. So, so this whole rectangle here is Q, this length here is P, and this AB is our X. So BW is P on 2, And so by Euclid 2.6, the square on AW equals the square on BW plus Q, which is this rectangle here. Okay? And again, we can see that because we just take this, we bring it up here, and then there's a square on AW. So that means that AB plus BW squared equals BW squared plus AHLG in our situation here. And then we just, this is X, this is P on 2, this is P on 2, and this is Q. And so then if we solve this, we take the square root of that, and then we subtract that. So yes, you're right, that should definitely be a plus right there. The minus here doesn't really matter, but that should be a plus. So Thabit bin Qura was an interesting person. Oops, I didn't. He was a Sabian, which was a religion, an extinct religion. It was one of the three religions of the three people of the book. Like there was Jews, Christians, and Sabians. They're no longer with us. I think he came from the area like between Syria and Turkey is now. And I think they all ended up eventually converting to Islam. But they were known as star worshippers. I think they believed in angels, they worshipped angels or something like that. They read, they were particularly fond of the Psalms. You know, in the Bible was written by David. So people of the book meant that, so according to, at that time, the sacred texts from our Bible would be the Torah, which is the first 5 books, the Psalms, and the 4 Gospels. They were considered sacred texts. And so as long as you followed those, you were tolerated at this point of time in this Islamic kingdom. The other thing that Thabit bin Ibn Qura was famous for was the idea of amical numbers. So we've seen perfect numbers. So who did number theory, Greek number theory? So you talked about perfect numbers, right? So that's the ones where, like for example, 6 or 28, where the sum of the divisors equals the number themselves. So people have done capstones on those. So related is the idea of an amicable number. For example, 220 and 284. So if you look at the divisors of 220, add them up, you get 284. You take the divisors of 284, add them up, and you get 220. So it's kind of like a little, whereas perfect numbers are kind of like a 1 cycle, amical numbers are a 2 cycle. You can generalize that to sociable numbers. So where, you know, here are 4 numbers. This is the sum of those divisors, that's the sum of those divisors, that's the sum of those divisors, and the sum of these divisors is back right here. So you get like a 4 cycle. So this is kind of neat. If you go to this website, I put there. So at the moment, the number of known amical pairs is like 1.25 billion pairs that they've found. So this is this is like one of those computer projects where you kind of can donate your computer spare time to help search for amical numbers, just like they're searching for Mersenne primes. So have people heard of GIMP? Right, so that's like the search for Mersenne primes. This is a similar kind of thing. So I think they're, at the moment they found all unequal pairs such that the smallest number is less than 10 to the 20. And so the next stage is looking for numbers less than 10 to the 21. So, anyway, it's an interesting little project. So he found, he had this theorem where if you had P, Q, and R primes of a certain form, then you can generate an amical pair. And this is very similar to that theorem that you did, right, for the perfect numbers. So if you found a prime of a certain form, then you can, if you found a Mersenne prime, then you can generate a perfect number. And so if you can find 3 primes of this form, then you can form an amical pairs. And this formula was actually later generalized by Euler, because he did a lot of things with amical pairs, numbers. So anyway, that was, this is just something that's a little bit fun. Okay. How are we doing for time? Okay, I've got enough time to do the next thing. Where am I? Here we go. Where is it? Oops, nope, gotta first get it up. Okay, so the next person that we're going, so basically we're looking at a list of Islamic scholars who studied algebra and brought it forward. And so the next person we want to talk about is Abu Kamil, who was, that's his name. So he was Abu Kamil, son of Aslam, son of Muhammad, son of Shuja. So he was just after Thabit, so he's like in the next generation, so we're talking late 9th century, early 10th century. And he was really heavily influenced by Al-Khwarizmi, and he was the one who actually brought forward that, you know, we should honor him, that he really is the founder, because at the time there were other people saying, you know, my grandfather actually started algebra, but he said, he was the one first succeeded in a book of algebra and who pioneered and invented all the principles in it. I have established in my second book proof of the authority and precedent in the algebra of Al-Khwarizmi. I have answered that impetuous man, Ibn Baza, on his attribution to Abd al-Hamid, who he said was his grandfather, which I thought was a kind of nice dig. So he's definitely in a chain from Al-Khwarizmi. I don't think he was that much influenced by Thabit bin Ibn Qura, but he went on to influence the next guy, Al-Karaji, who we'll talk about next. He's very, very important in making algebra more like the algebra they have today. And Fibonacci, who we've all heard about, and when Fibonacci introduced numbers and algebra to Europe, he actually used Abu Kamil's book. And his was the basis for his famous book, Liber Abaci. We'll see that later. And in fact, when he wrote his book, he called his book Kitab al-Jabra wa al-Muqabala, the same name that Al-Khwarizmi used. So he was thinking himself as updating Al-Khwarizmi. And there's another important difference as well. When Al-Khwarizmi wrote his book, he wrote his book as a general textbook for like teaching you know, like for high school students or the equivalent, right? This was like for the general public. He wanted to introduce the ideas of the Hindu numerals and the way of doing algebra. His book, Abu Kamil's book, is definitely more of a book which was for other mathematicians. So it's kind of like at a higher level. So he did, in the first part, he did the solution of quadratic equations, very much what we've been talking about, like the 6 cases, including the 3 that we would consider proper quadratics. And then later on, he talked about problems with the pentagon and the decagon, and we've already seen that this is kind of, that the pentagon and the decagon are kind of interesting because they can be constructed and you can kind of do algebra with them. And then his last section was working with Diophantine equations, kind of indeterminate equations. So remember what an indeterminate equation is. It's something like, you know, ax plus by equals c, for instance. So it just doesn't have one unique solution. There'll be like a smaller solution, and then you can generate, you know, there's going to be an infinite family of solutions to that problem. So he really did advance the field. So for one thing, he worked, Al-Khwarizmi and Thabit only worked with powers up to x squared. Okay? And it's important that you kind of deal with more general powers to get sort of break free from geometry. Okay, so the reason why they only went up to x squared was they were only interested in geometry. They were only doing things in the plane, right? And so, you know, in theory, you could have x cubed because that would be talking about volumes, but there was a kind of reticence to talk about higher powers. But he did that. He kind of understood this basic principle here, right? That if you multiply 2 powers together, then you add the exponents. He didn't explicitly say that, but you can see that he knew that because if you look at how he called powers. So for example, x to the 5th, he would call that, so again, right, they didn't have these symbols, so they just used words. So the word he used to describe this was mal shay, right, which is wealth thing. So that's x squared times x. So he knows that this is x to the 5th. And he called this, he called cube, and x to the 8th he called mal. So x squared times x squared times x squared times x squared. He wrote down rules which would kind of be, you would find in like an algebra textbook. So things like, you know, a plus or minus px times b plus or minus qx, you would multiply it out, kind of like this. Although he did it in words, and when you look at his words, we would find it a little bit confusing. Like he says, when roots are added to numbers or subtracted from them, on whichever side they are arranged, then the 4th part is added. So this means this, right? So roots are added to number or subtracted, i.e. here's a number, here's some roots, we either added or subtracted, and we're multiplying by it. And whichever side they are arranged, i.e. it doesn't matter whether you're talking about a plus px or px plus a, then the 4th part is added. So this is the 4th part, and all he's saying is that this sign here has to be a positive. So if both of these are negative, this is positive. If both of them are positive, this is positive. And he doesn't actually talk about these other signs here, the first part, the second part, and the third part, because that's just understood that you would know that. That's kind of interesting. So he did actually have explicitly write down the rule of signs, which is important if you're doing algebra, right? That minus times minus is a plus. So, and the way he said it is, the product when two terms are subtracted is added, the subtracted times the added is subtracted, the added times the added is added. So that is how he would state the rule of signs. And then another interesting thing is he did manipulations with irrationals. So this one here, we will recognize straight away. Okay. And so this meant that, if you had square root of 5 and the square root of 7, don't figure out the square root of 5 and then multiply that by the square root of 7, which you figured out. You can just figure out the square root of 35. This is just making life easier for you, just like accumulating square roots. This one is a little bit more, but this is actually, you can derive this from just, a plus b squared and reinterpret it, you can get this. But we'll see later how you can use this. And also, he did things like this. And he would actually go ahead and prove these things. Okay? And he would prove these things by kind of arithmetic ways, by, just using commutativity and distributive law, but also he would prove it by geometric ways. And I think I want to stop here because I think we've gone far enough. And we will continue this next week, looking at some of these problems.